Welcome to my YouTube channel. In this video we are going to be looking at rotational motion part 1. What we are going to be looking at is the rigid body undergoing rotational motion. So we have a diagram that describes a rigid body undergoing rotational motion. So we notice that if the rod moves from this point to this point, it covers an angle theta, and the arc traced is given as S, right? So the connection between the arc S, theta, and the radius of the rod R is given by this expression here. So S equal to R theta, or theta equal to S all over R. Okay, so we have our theta as the angular position, omega is the angular velocity, alpha is the angular acceleration, right? So the expression for angular velocity is given as W equal to d theta over dt. Then the expression for angular acceleration is given by alpha equal to dw dt, right? So we can also look at equation governing a body undergoing rotational motion in terms of the initial angular velocity and final velocity, as well as the angular acceleration. It has a connection with the equations governing linear motion. Okay, so we can look at another equation which we are familiar with in linear motion. This is our theta, which is the angular position, equal to half of initial velocity, angular velocity, plus final velocity, angular velocity times time. Then another formula we are familiar with is this one too. Then we also have this particular formula. Okay, so we'll move on to the next stage where we have this particular formula which has been derived earlier, where this one is the S, the radius, the arc, and the angular position. If we differentiate this one with respect to t and differentiate this one with respect to t, we have a new term where this our r is a constant. We have something of this form, ds dt equal to r d theta dt. Now remember, this is our velocity, this part is our angular velocity, and that gives us v equal to rw. Our v here is more or less like the linear velocity of the water particle or the body that undergoes rotational motion. Okay, so if we differentiate this one with respect to t also, we have our acceleration and we have angular acceleration, and that gives us 8 tan a subscript tan equal to r alpha, right? Okay, so we can also find the inward acceleration, which is given from this expression, F equal to ma equal to mv squared over r. That is, the sum of all the forces acting on the body must be equal to this particular expression, mv squared over r. So if we cancel this our m, it gives us a rad equal to v squared all over r. So we have two types of acceleration, which is the tangential acceleration and the radial acceleration, and it can be seen from this diagram. Now from this diagram we can see that this tangential acceleration is the one pointing in this direction, while the radial acceleration is the one pointing inward. The resultant of this one and this will give us this particular a. So, and that can be shown in the next slide. But remember, we can replace this v squared, which is our v, with rw, so it becomes r squared w squared. R will cancel r, and that gives us w omega squared r. So now that we have our radial acceleration as v squared r equal to this, then we can now bring our radial acceleration in this simpler form of this form. So the resultant acceleration will now be equal to a equal to the tangential acceleration squared plus the radial acceleration squared. So anytime we're asked to find the acceleration and it's not specific, we'll use this formula to find, first of all, find the tangential acceleration and the radial acceleration. But if we are asked to find the tangential acceleration, we know the formula to use, which is R alpha. If we are asked to find the radial acceleration, we know that it is this one that we are supposed to use. So let's look at the problem, and let's see a typical problem. Now, if the angular acceleration of an object, right, undergoing rotational motion is alpha equal to this, find the magnitude of the acceleration at the instant when the angular velocity is 10 rad per second if the radius is 0.8. So in this case, we have to find the magnitude of the acceleration as this, right? So we need to find this and find this. So to find this one, depending on which one we want to find first, we know that this one is alpha times r, and since we are given alpha, we'll multiply by r. The tangential acceleration is given by alpha r, and we know our r to be 0.8, and the angular acceleration is given by 50. Then by the time we resolve, that gives us 40 meters per second squared. So to find the radial acceleration, we use r, which we already know to be 0.8, then omega squared, which we already know to be this. Then we'll substitute the value in, and as a result we get 80 meters per second squared. So our final acceleration will now be the square root of the tangential plus the radial, which is 89 meters squared, 89 meters per second. Okay, so let's look at energy in rotational motion, energy stored in rotational motion, right? So we'll consider this figure. This figure is a single body, but can be split into several particles. So we can call this one M1, M2, M3, and M4. M1 has a distance from the center of rotation, the axis of rotation, as R1. M2 has a distance from the center of the axis of rotation, R2, likewise R3 and R4 and Mi, right? So we notice that the energy of each of these mass will be half of M1 V1 squared. So plus, because they are all forming a single body, we need to add the kinetic energy of this, kinetic energy of this, kinetic energy of this, and that gives us half of Mi Vi squared equal to half of Mi, because our Vi is already Ri squared W squared, right? And that gives us summing all of them. If we take I to be 1, 2, 3, and so on and so forth, but what we notice is that Wi is common to all of them. They rotate at the same angular velocity, so we can factorize that one out and leave this part here. So when we sum these parts can be called a new term called I, and this I is called the moment of inertia of the body, which is given as MIR squared. So we can now replace this one with I omega squared, and that gives us this expression. So this is how to derive the kinetic energy of a body undergoing rotation, and it's given as half of the moment of inertia plus the angular velocity squared. It's important you remember this formula because we are going to use it later. Now these are lists of different shapes and body with their moment of inertia. You might be interested in calculating a particular one of these particular body undergoing motion, and you will need the moment of inertia. So this one is hoop about central axis. It's rotating about this point, so the moment of inertia is mr squared. This one, the center of rotation or the axis of rotation, is along this direction, so the moment of inertia is half of m r1 squared r2 squared, where we have the inner radius and the outer radius. So the same thing also goes to all of them. So you can pause the video and take note of all this moment of inertia for the different shapes. Okay, so the next thing we want to look at is translational and rotational energy. Now what that means is that we can have a body that is rotating about an axis, We can also have a body that is moving from one point to another point, and we can also have a situation whereby a body is rotating and at the same time moving from one point to another, which is called rolling, and that's given by this diagram. So we can see that this one is pure rotation. This particular axis is fixed and this body is rotating in this direction. It's rotating in this direction. This one is another scenario where this body does not rotate, but it moves from one point to another. That kind of scenario is said to be translational, or we say the body is undergoing sleep. It sleeps, right? So if you combine this and this, it gives you this particular one, which is rolling. They call it rolling. So it means that it is rotating and at the same time moving from this point to this point. So the kinetic energy for this particular system is given as this, which we have derived for rotation, while the kinetic energy for this particular translational is given by this, which is half of mv squared when there is sleep, while the kinetic energy for this particular one is a combination of rotational and translational, which is given as this. How that's okay. Let's see if we can look at one or two problems, and then we'll see. So this is a typical example of a problem that can arise from this one. Remember that your v squared is what? Your w r, right? All squared. So the question is, what is the ratio of the rotational kinetic energy to rolling kinetic energy of a solid sphere? First of all, we must note what they are talking about. The shape is solid sphere. So they said, what is the ratio of the rotational, which is this one, this, to rolling. So what's the ratio of this to this? Ratio of this to this. And we notice that there is moment of inertia here, moment of inertia here. We need to know the moment of inertia of a solid sphere for us to be able to solve this problem. So let's go into this first before taking care of this one. So the moment of inertia of a solid sphere is given by 2/5 mr squared. So if you substitute this into the kinetic energy of a rotating sphere, we have rotational kinetic energy is equal to half of iw squared, which is this half remains here. I is 2/5 mr squared dot omega squared. That's that. So if this 2 takes care of this 2, we are left with 1/5 mr squared w squared, and that gives us 1/5 mr squared w squared. Okay, so the next thing we look at is the rolling, and the rolling is given by kinetic energy equal to half of mv squared plus half of iw squared. Now, since we know our I, we can substitute the value of I as this expression into this part here, and that gives us half of mv squared equal to half of 2/5 mr squared w squared omega squared. We can take care of these two. That will give us 1/5. Then we can replace this v with r squared w squared, and that gives us half m r squared w squared plus 1/5 m r squared w squared. If we simplify this one by factorizing m r squared, we'll be left with half plus 1/5, and that gives us 7/10. So the rolling kinetic energy is given by this. Now that we have this and we have the rotational, which is this particular one, so we can see the ratio of this to this is what we are looking for, and that is given by rotational kinetic energy is to rolling kinetic energy, which is given by this expression is to this expression. We can cancel everything here out, cancel, leaving 1/5 divided by 7/10, and that gives us 2:7. Hope that's okay. Hope this helps. Thank you for watching. Please like, share and subscribe to this channel. Thank you.